Hello everyone. In this video we will see how to calculate object code for the following SIC program. This is a program that will be given, and these are the opcode values for their corresponding mnemonics. These are the given values, and for using these values and for this program we need to generate the object code. So let us start. Let us consider the first statement that says sum start 0. That means the name of this program is sum and it starts at the location 0. 0 is the location in our memory. The location counter table hence will be updated with 0000 because it is represented in a hexadecimal format. It occupies half bytes, that is 4 bits. Why are we writing over here, not over here, is because the program says that end first. That means this first FIRST is the first executable statement, and we are going to end is what it says. So the first executable statement is this first LDX #0, and that's why we are going to start our program from this location, and this is the first executable statement. And since start is an assembler directive, there is no need for us to generate object code for that. Let us go to the next line statement, that is LDA #0. Before that, this statement, we need to check this statement. First LDX #0. This is a format 3 instruction statement, and hence it occupies 3 bytes. Format 3 instruction. So we are going to add 3 bytes to this location counter table, and the value, the memory is 0003. So the next statement, that is LDA #0, starts from this location is what is the meaning. And this statement also is a format 3 instruction, and that is the reason why we have written 3 bytes over here. This instruction occupies 3 bytes, and so the next instruction will start from 0006. 3 plus 3. 003 4 5 6 is the next location where this statement will start. So it is plus LTB hash table 2. So this statement clearly is a format 4 instruction statement because there is plus written over here. This means it is a 4 byte format 4 instruction, and it occupies 4 bytes, and hence we are going to write 4 over here. So we are going to add 4 bytes to this location 0006. It forms 000A. Let us see the next statement, that is base table 2. This is a statement that says that base table 2 is using the base register, and the value of table 2 will be stored in the base register. And since it is an assembly directive, there is no need for us to generate object code. So it doesn't occupy any memory location as well, and so we are going to our next statement, and this statement starts from 0008 because we are going to add 4 for this memory address, and it starts from here. This statement starts from 000A, and this statement is a format 3 instruction, and hence we are going to add 3 bytes to this memory location, and hence it is going to be 000D. This statement is also a format 3 instruction, so 3 bytes we are adding, it forms 0010, and this statement is a format 3 instruction as well, so we are going to add 3, 0013 is the result. And then this statement JLT loop is also a format 3 instruction, so we are going to add 3, and the next memory location is 0016. So this statement, there is plus over here, and hence it is a format 4 instruction statement. It occupies 4 bytes, so we are going to write 4 bytes over here, and hence we are going to add 4 bytes to this memory address location 0016, and it forms 001A. It is 1. 001A. This is a format 3 instruction, so it occupies 3 bytes, and we are going to add 3 bytes to this, so it forms 001D. This is a variable count that occupies one word. We are going to reserve one word of location to this variable count. That is the meaning of this statement. There is no need for representing it in any format. These are all declarative kind of statements. So we are going to reserve one word for this variable count. Okay. So it occupies 3 bytes. One word is equal to 3 bytes, correct? So it occupies 3 bytes. So we are going to add to this location 001D plus 3 forms 0020. And this statement as well says that table is a variable for which one word is reserved. Okay, one word means 3 bytes is reserved. And then adding it to this location form 0023, and this says that table 2 is a variable that is reserved with these many number of words. But this is represented in a decimal format, and hence we need to change it into hexadecimal format, which forms 1770. When 2000 is converted to hexadecimal format, it becomes 1770. Okay, so that we are going to write over here. It occupies 1770 bytes. This statement occupies these many number of bytes. So we are going to add to this memory address 0023. So the next statement starts from this location is what is the meaning. 1793. Okay, 1770 plus 0023 forms 1793. See the next statement. This statement also occupies this many number of bytes, this many number of decimal bytes. So we need to convert it into hexadecimal format, which forms 1770 bytes. Okay, so this, when added to this memory address, we get this as an answer, 2F03. Add 1793 plus, this is a hexadecimal mathematical calculation which we do. We are going to add these two hexadecimal digits, and hence we get this answer. Okay, so the next statement says that there is nothing variable over here. We are only reserving one word. One word occupies 3 bytes. So we are going to just write 3 bytes and add to that, and this forms 2F06. So this is the last address. This is the last address of this program. Okay, there is no need to mention anything for this because it is a assembly directive. AND is an assembly directive, right? There is no need for us to generate object code, and it doesn't occupy any location in the memory. So this is how we are going to write the location counter table. Now we will see how to generate object code for each of these statements. Okay, so let's start with the first statement, that is first LDX #0. Let's start. So this statement clearly says that it is a format 3 instruction, right? And the opcode value for LDX is 04. 04 is the opcode value, 04, and that when represented in bits forms 0100. Since it is a format 3 instruction, we are going to use the first 6 bits, and hence this is the opcode value. And then what is given over here, it is given that #0. #0 means it is using immediate addressing mode, and this itself is the displacement value. Okay, so let us represent it over here to generate our object code. What is the opcode value? 000001. Okay, this occupies 6 bits. And then let's go to the flags NIX, BPE, and this is the displacement field which occupies 12 bits. Okay, so these all occupies 1 bit each. So it is not indirect, but it is an immediate addressing mode. That is why we write in this way. It is not indexed, it doesn't use any of the counters, and it is not a format 4 instruction. So what is the displacement? Immediate value, that is 0. since it occupies 12 bits, we are going to fill it up with the zeros. So let us generate object code now. Right? So this forms 0 and this forms 4, 5. Correct? 0, 0, 0, 0. So the object code for this statement is 0, 5, 0, 0, 0, 0. Okay? So that is what we are going to write over here. 0, 5, 0, 0, 0, 0. Okay? This is how we generate object code for this statement. Moving on to the next statement, that is LDA has 0. This is also an immediate addressing mode statement. That means I will be set to 1 and N will be set to 0, and it uses the immediate value as displacement. LDA value is 0. Load into accumulator is 0. So that is what we are going to represent in bits. 4. Take the first 6 bits and generate the object code using the format 3 instruction. This is a format 3 instruction, correct? So fill it up with 6 zeros. This is the opcode field, and write the value for NI, X, B, P, E, and this forms the displacement, okay, which occupies 12 bits. What is this? 0, 1, 0, 0, 0, 0. It is only immediate addressing mode. It is not indirect, not indexed, doesn't use any of the counters. It's not format 4. And what is the displacement value? It's just the immediate value. So it is going to be 0. Okay. So what is the object code now? Is 0, 1, 0, and these are 3 zeros. Correct. So the object code for this statement is 0, 1, 1, 2, 3, 4. Okay, this is the object code. Let us write it over here. 1, 3, 4. Okay, now moving on to the next statement. Plus LDB hash table 2. So this is a format 4 instruction. Right? It's a format 4 instruction because plus is written over here. And it is a instruction that uses immediate addressing mode. There is hash present over here. Right? And what was represented over here, that it is using base counter. Okay, so let us generate the object code. And what is the value for LDB? The opcode value for LDB is 68. So that we are going to represent it in bits, which forms 0, 1, 1, 0, 1, 0, 0, 0. So the first 6 bits we are going to take, and we are going to represent it to generate the object code. Since it is format 4 instruction, it occupies, the address field occupies 20 bits, as we know. We will see that later. 0, 1, 1, 0, 1, 0 is the opcode, which occupies 6 bits. We are going to take first 6 bits, correct? And then we are going to set the flags N, I, X, B, P, E, and this is for the address, which occupies 20 bits. And now this is an immediate addressing mode, right? So we are going to set it 1. This is 0. It doesn't use indexed addressing mode. It doesn't use any of the program counter counters, and hence it is set to 0. And this is a format 4 instruction, and hence we set it to 1. And what is the address? Address is whatever is there in table 2. What is there in table 2? I mean where it is located. Table 2 is located at 0023, right? So that is the address. Immediate whatever is the value for, where the table 2 is located, that will form the address. So we are going to write, but it occupies 20 bits, correct? But this is, table 2 is a statement label where this 0023 is the address where it is located. It occupies only 16 bits. So we are going to add 1 0, that which occupies 4 bits, that is 0000, and then the bits representation for that hexadecimal location, location. Table 2's location is 0023. That we are going to write it over here. 0, 1, 2, 3, 0. And now for 2, 0, 0, 1, 0. And now for 1. Okay, this is how we represent. Now we are going to group it together to get the object code. So what is the object code? This is 6 and this is 8 and 1, 9. This is 1, 0, 0, 0, 2, 3. Okay, what is the object code now? 6, 9, 1, 0, 0, 0, 2, 3. Okay, this is the object code. Let us write it over here. 6, 9, 1, 2, 3, 2, 3. Okay, this is the object code for this statement. Now moving on to this statement, as I said earlier, this is an assembler directive and there is no need to generate object code and it doesn't occupy any of our memory space. It is present by default. So let us move on to the next statement. Loop add table comma x. Okay, this statement we will see. Loop add table comma x. What is the opcode value for add? The opcode value for add is 18. Opcode value for add is 18. So we are going to write it in bits format. 1000. Take the first 6 bits because it is a format 3 instruction. Okay, and we are going to represent it in our format 3 instruction. 000110. It occupies 6 bits, correct? And what are the values for NIX BPE? X BPE format 3 and hence displacement, which occupies 12 bits. Okay, so we see the statement which says that it is neither indirect nor immediate. It is it's a statement that uses indexed addressing mode and it uses program counter because by default it uses program counter, correct? That is the reason. And also it is not a format for instruction. And what is the displacement? That we need to calculate. Displacement is equal to target address minus program counter value. What is the target address for table? Where is it located? Table is located at this location 0020. 0020. What is the value for program counter? Look at this statement. Loop add table comma x. This statement's next executable instruction is present at this location. This is the value of program counter 000D. Okay, 002D. Sorry, 0020 minus 000D. What is the value we get? Minus 000D. Okay, how do we subtract it? It forms 16. 16 minus what is the value for D? B is 11, C is 12, D is 13. 16 minus 13 is 3. Correct? So, it forms 0. This is the displacement value. Okay? So, we are going to take only the last 3 digits because it occupies 12 bits and denote it over here in bits format. 001 and 3's value is 11. Okay, so let us generate object code for this. This is 1, 1, 8, 9, 10, 11. B, this is 8, 9, 10. A, and this forms this value 0, 1, 3. So object code now is obvious. 1B A 0, 1, 3. Okay, let us write it over here. 1BA 0, 1, 3. This is the object code for this statement. Moving on to the next statement, add table 2 comma x. Okay, table 2 comma x. But see here, table 2 uses base register. So keep that in mind. What is the value for add? Opcode value for add is 18, right? So opcode value for add is 18. How are we going to represent it in bits? 0001, 1000. Take the first 6 bits. That is done. Okay. Now we have to see that this uses base register. So we'll see that how to calculate displacement using base register. First we will write the format in which it is represented. So first is opcode, which occupies 6 bits. First 6 bits, 1, 2, 3, 4, 5, 6. This one I have written. Okay. NIXBPE. This is displacement, which occupies 12 bits. So this is neither indirect nor immediate. It uses indexed addressing mode. It uses base counter and doesn't use program counter. It's not a format 4 instruction. So now we have to calculate the displacement. Displacement is equal to target address minus base counter value. Base counter, right? We are using base counter over here. It's not so clear. I'll write it again. Base counter value. What is the target address? Where is it located? Where is table 2 located? Table 2 is located at this location 0023. Correct? 0023. But over here, just observe base to table 2. This says that base register contains the value or the location where table 2 is located. So that means that our base register contains this value, table 2's value. Table 2 values, I mean that the location where table 2 is present. So this is 0023, right? So the displacement will be 0. Fill it up with 12 bits and generate the object code. What is the object code? 1, 8, 9, 10, 11, 8, 9, 10, 11, 12, 12, 0, 0, 0. Okay. What is the object code now? 1B, C, 0, 0, 0. Okay. This is how we generate the object code. 1B, C, 0, 0, 0. Now moving on to the next statement, TIX count. Okay, let's see the next statement. TIX count. What is the opcode value for TIX? TIX's opcode value is 20. Okay, so we are going to write it over here and represent it using bits format 1, 0, 2, 3, 4. Okay, so take the first 6 bits. Okay, and now this clearly is a format 3 instruction. It's a format 3 instruction, and hence we have to calculate the displacement. Correct? What is the displacement? Displacement is target address minus this. We are using program counter because it is not mentioned that we need to use base counter and it doesn't exceed the maximum value. So what is the target address for count? Where is count present? Count is present at 001D. 001D. And what is the program counter value? TIX counts. Next executable instruction is 0013. It is present at that location. Okay. When we subtract it, what is the value we get? What is the value for D? D's value is 13, right? 13 minus 3 forms 10. 13 minus 3 is 10. So the answer is 000A. Okay. This is the displacement value. Is it clear? So this is the displacement value. Let us now represent it to generate the object code. Okay. So the opcode is 001000. This first 6 bits. Okay. And then N, I, X, B, P, E, and this is the displacement field occupying 12 bits. Okay. So what is this? This is neither indirect nor immediate. Doesn't use indexed addressing mode. it doesn't use base counter addressing mode. It uses program counter, and it is not a format for instruction. And what is the displacement? Last 3 digits 00A, that you need to write. Okay, what you are going to get is 00A. So we generate object code for that. What is this? 2 2 3. This is also 2. Okay, the object code now what we get is 23200A. This is how we generate the object code for this statement. Let us write it over here. 23200A. 23200A. Okay, let's move on to the next statement, JLT loop. JLT loop is over here. What is the value for JLT? Opcode value for JLT given is 38. And how do we represent it? 00111000. Take the first 6 bits. Okay, that is the opcode value. Now we have to calculate the displacement. This is a format 3 instruction. We have to calculate the displacement. Before that, let us write the format, and then we will move on to calculating the displacement value. 001110 is the opcode value. N I X B P E displacement 12 bits. Okay, this is a instruction or statement that doesn't use indirect nor immediate addressing mode, doesn't use indexed addressing mode, and it doesn't use base counter. It uses program counter. It's not a format 4 instruction. Now what we have to do? We have to calculate the displacement value, which is equal to target address minus program counter value. What is the target address? Where is loop present? Loop is present at the location 000A. 000A. What is the program counter value? JLT loop is a statement, right? And the program counter value is 0016. 0016. So this is a negative subtraction, hexadecimal subtraction. How do we do that? 0016 minus 000A. This is how we subtract. What is the value we get? We are carrying over here, which forms 16 plus 6 is 22. 22 minus A, that is 10. Okay, is 12. 12 is represented as C. So minus C is the value we get. That we need to represent it in 2's complement. Correct? In SIC program, this is how we represent the negative values. So when we calculate the negative value, what are we going to get? What are we going to get when we calculate the negative value for that? It is FF4. Okay, you just do it. You write the 1's complement and add 1 to that. Okay, write the 1's complement for this value, add 1 to that, and then we get this value FF4. Okay, this is the displacement field FF4. You need to write the bits representation, corresponding bits representation for this value. Now let us generate the object code. Okay, for your reference, I'll just write it out over here. F1 2 3 4, this F, and this is 0 1 0 0. Got it? So what is the value for this? Is 3, and this forms 8 9 10 11 B. This is 2 FF4. Object code clearly is 3B 2 FF4. Okay, so let us write it over here with statement JLT. 3B2 FF4. Okay, so we got the object code for this statement. Let us now move on to the next statement, plus STA total. This is a format 4 instruction. Okay, it occupies 4 bytes. What is the value for STA? STA's value is 0C. Okay, so STA's value is 0C. How are we representing it? 00001100. So take the first 6 bits. Okay, that is the opcode value. Next, it is clearly a format 4 instruction because there is plus present over here. So the address where this is located, total is located, that is what is the address field. Where is total located? 1793. Total is located at this location. So that itself will become the address field. There is no calculation of displacement or anything. Target address itself is what we have to mention in our format 4 instruction. So let us write the opcode value 3411. Okay, opcode value which occupies 6 bits. N, I, X, B, P, E. This is the address field which occupies 20 bits. Okay, this is neither immediate nor this is neither indirect nor immediate. It doesn't use in-text addressing mode. It doesn't use base counter. It doesn't. It uses program counter. It is a format 4 instruction. Okay. No, format 4 instructions doesn't use any of the counters. So it is 0. What is the address field? That is the location where total is present. Total is present at this location 1793. 1793. But this is a field that occupies 20 bits. So we are going to write 0 over here. Corresponding bits format is represented in this way. 1. For 7 it is 0, 1, 1, 1. For 9 it is 1, 0, 0, 1. 8 plus 1, 9. And for 3 it is 0, 0, 1, 1. Okay, this is how we represent. Let us calculate the object code. This is 0, 8, 9, 10. This is F. All are set to 1, right? F. This is 1. So the object code is 0F1 01793. Okay, that is what we are going to write. It is 0F101793. Moving on to the next statement, R sub. R sub. R sub is a format 3 instruction that occupies 3 bytes. Let us represent it in the bits format. No, in the format 3. And what is the opcode value for R sub? R sub's opcode value is 4C. It is given over here. 4C. Okay. So represent it 0, 0, 1, 0, 0. And C is 1, 1, 0, 0. Take the first 6 bits. Okay. What is the value? 0, 1, 0, 0, 1, 1 is the opcode value. Correct. So N, I, X, B, P, E, displacement. Okay. What is the value for N? It is all set to, yes, it is all set to 0. I made a mistake over here. It is neither immediate nor it is neither indirect nor immediate, right? We have to write 1, 1 over here. It is not indexed. It doesn't use any of the program counters, and it is not a format 4 instruction. And the displacement, since there is nothing present over here, no calculation need to be done. It is just return to the caller. R sub means that. So displacement will be 0. Fill it up with 12 zeros. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. So generate the object code now. 1, 2, 3. It is 4F0, 0, 0, 0. So the object code now will be 4F0, 0, 0, 0. Okay. Let us write it over here. 4F 1, 2, 3, 4 zeros. Okay. So the next statement is count reserve word 1. Reserve one word for this count variable or for this label count. So these statements doesn't use any of the formats for its representation, and since they are assembler directives, there is no need to generate object code. Okay, there is no need to generate object code. So all the values we got it right, we calculated using these values the object code. So that is how remaining all the statements, there is no need to calculate the object code, correct? So this is how we calculate the object code for this SIC XC program. Okay, this is the object code. So using these object codes we can generate the object program as well. Okay, if in the question only the object code has been asked, that is the reason I'm not showing the object program representation. So for this question this is enough. Okay, I hope it is clear. Thanks for watching.